first idea to having cyclotron in Warsaw was in 1930. Two eminent Polish professors, Andrzej Sołdan and Stefan Pienkowski, argued why in Warsaw University physics faculty should have the cyclotron. They start collecting money to buy such a cyclotron, but after Second World War, it was not possible to continue this project, and we had to wait until 1972. Then the government decided that in Warsaw will be a cyclotron accelerating heavy ions. Why heavy ions, not light ions, for example? Because at that time in Kraków, they use cyclotron accelerating light ions. That's why it was decision not to duplicate cyclotrons in Kraków and in Warsaw. Decision was preceded by 4-5 years of discussion in the Polish physics community, and finally this community decided we would like to have cyclotron based on U200 cyclotron, which was in Dubna. It is not the same cyclotron. U200 is the base for designing our cyclotron. There are two different cyclotrons, even if they have similar names. And in December 72, two groups from Poland, one group from Świerk, second one from Faculty of Physics, went to Dubna and collaborate with Dubna team with this project for cyclotron. And after 5 years, the cyclotron components, but not full cyclotron, only some components brought from Dubna were stored in the temporary facility in Warsaw. And this facility you can find on this picture. It looks like cyclotron, but it's really not cyclotron because, for example, RF system was not existing at the time and was built as a collaboration between Warsaw University and Świerk Center. What about the building? Because cyclotron components were existing, and we should start from cornerstone laying ceremony. It took place June 11, 79. On the right side, you see 3 numbers, and here you see who was under this number. So first was rector of the Warsaw University. Professor Jerzy Kołodziejczak was president of the Polish Academy of Sciences, and Professor Choiński was director of the Świerk, but now it is Nuclear Center for National Center. Okay. Earlier it was different name, but you know we have difficult history, so from time to time the same center changed its name. And after 10 years, you can find our building. It looks now exactly the same, but this part is not possible for access because new physics faculty is occupying this part. So this is historical picture. And what we have in our cyclotron vault, this is status in April 1992, cyclotron. Okay, but nevertheless, maybe it's working. No, no, okay. Okay, so we have cyclotron at that time. Cyclotron at the time was equipped with internal ion beam, and here you see first switching magnet with few beam lines leading to experimental hole. So first internal beam we received in November 22, 1993. In this case was neon beam with very low energy because we were worried about some problems in magnetic field. So it was decided to use very low energy beam, and then it's safe a cyclotron if we need to open it and move some replacement or repairing. After a few months, on April 8, 1994, first beam was extracted. In that case, it was nitrogen beam with energy 31 MeV, and this beam is visible. This point, it is not a mistake in the field, but it is beam touching some screen inside. After that, we decided to start opening ceremony. It was May 2094, and His Magnificence of Director, University of Warsaw, opened our laboratory. Here, some of you know exactly this picture, but some of you not. This is scheme showing what we have in our building. So cyclotron vault is easy to recognize. On the left side, we have dedicated vault for cave A. In the early beginning, it was decided to collect equipment for for medical radioisotopes production system, but we never installed this system here, and now we use this cave for biology experiment mainly. Experimental, as you see, we have few cases. In each cave, we have permanent experimental setups. Of course, in some cases, these experimental setups can be modified with user equipment. And this system part is devoted for nuclear reaction research only, in fact. But coming back to cave A, as you see, the cave A is ended with beam line. So research group which has own equipment can be attached to this beam line, and it's worked quite well, such a solution in our case. But coming to the radionuclide production, I should come back to the cyclotron vault, where we constructed a station for irradiation targets with an internal ion beam. This was very simple station. I named it version number 1, which operated between 1998 and 2016. We start out this operation producing sodium 22 and sodium 24 for the need of a laser group, which was also located in our building. And here you see the nuclear reaction used for this kind of radioisotope production. Of course, they are not for medical application, but for laser research works. But after a few years of experience, we decided that it's pity to have such simple station. We should replace it with completely new design. And now you see present status of this station. It is designed as much as possible to be automatic. So in fact, for the operator, he needs or she open this cap, put by hands target, in this case, tilt target into the target head, close it, and come back to the control room to obtain vacuum, open gate, move target to the appropriate radius inside the cyclotron, and after that, come back to this chamber and release target up to black box located on the remotely controlled trolley. This is realized automatically, so it looks quite well and work quite well. What we can irradiate, we can irradiate metallic target or target like powder. It's also possible to irradiate. Of course, during irradiation, we control temperature, we control time, we control current touching the target. And our experience with heavy ion laboratory in case of involvement in medical radioisotope production means mainly we did it to produce astatine-211 using this nuclear reaction, but also we produce scandium-43, scandium-44, titanium-44, selenium-72 as a generator case. All of them with alpha beam. In our case, alpha beam can reach energy up to 30 to 33 MeV. Another our possibility, it is radiopharmaceutical production and research center, which valuably expanding here research capabilities. What it is? Let's start from the signing ceremony of the contract. It took place at the IAEA headquarters in October 23, 2007. And this site means is located here, red border marked this pharmaceutical company or site, which is part of our laboratory, but for FDG production, this site is operated by commercial company, not by heavy ion staff. What we have, from our point of view, the heart of this system is the commercial cyclotron dual beam. It's this cyclotron from GE, PET trace. It means that proton can reach 16.5 MeV with current up to 80 microamps. This limitation is coming from the license which we have for the cyclotron. And we can accelerate deuterons, maximum energy 8.4 MeV and current limit like 60 microamps. As you see on the right side, to the cyclotron we have connected a few different targets, 2 targets for fluorine-18 production, 1 target for oxygen-15, and two targets for carbon-11 production. And the second port is dedicated for external target station. And our first target station you can find here. This is result of executing as a heavy ion laboratory the grant alternative methods for the 99 technetium production. This grant was dedicated to the consortium. Main leader consortium was Polatom, National Center for Nuclear Research, and Professor Mikołajczak was the leader of this project. Our responsibility was to produce technetium 99N. A grant finished in 2015. Fortunately, after that, again the same consortium, but the leader was changed to Institute of Nuclear Chemistry and Technology. The name for this grant, the development of methods for production of new radiopharmaceuticals based on scanning radionuclides used in positron tomography. Founding institution was the same as previously. It is National Center for Research and Development. Our responsibility was to produce SUC, scanning 43, scanning 44. And this station is present now. And what I can say more? Okay, since 2022, we have been implementing another grant. The title for this grant is Development of Free Photon Emitting Radio Tracers for Positron Imaging. And our responsibility is to produce scandium-44, cobalt-55, and arsenium-72. Why? Because Jagiellonian University people developed new tomograph, novel free photon tomography, and this grant obtained from the Jagiellonian University, University of Warsaw, and Institute of Nuclear Chemistry and Technology. So, summarizing, in case of this site, between 2016 and 2025, we produced 8 isotopes, as you see here, so scandium, vanadium, cobalt, arsenium, zirconium, technetium, lanthanum, and mercury. This is our experience, and I hope I show you where we were involved during this, let's say, 20 few years in case of production radionuclides, also for medicine. Thank you very much.